This is now the 5th lecture of the condensed matter course. In the first 4 lectures, we studied vibrations in solids, and we studied electrons in metals. And we learned quite a bit about these topics, but we also developed a rather long list of puzzles, things that we couldn't understand. I wrote a list of them at the end of last lecture. Some of them included the sign of the Hall coefficient. We couldn't figure out why it sometimes has one sign, sometimes has another sign. We also had a rather unreasonably long mean-free path in Sommerfeld theory. We couldn't understand. And if you go back to earlier in Debye theory, there were also some puzzles there. We didn't understand why it was we introduced an ad hoc cutoff. We had some motivation for it, but it was certainly an ad hoc prescription. And all of these problems stem from the same place, and the same place is that we're not taking seriously the microscopic structure of materials. We're not really considering that they're made up of individual atoms, and the atoms are bonded together in very particular and often periodic ways. So much of the remainder of the term is going to be devoted to understanding how the microscopic structure of materials affects its macroscopic properties. But before doing that, it's probably worth backing up and understanding why it is that the atoms stick together in the first place to make the materials. So this brings us to the domain of chemistry. And as much as we hate to admit it to both our friends and our enemies, chemistry actually is interesting. It's an important subject both scientifically and it's certainly industrially, technologically, and it actually has some fundamental deepness to it as well. And you could certainly spend 3 or 4 years studying chemistry, or even longer, and we're going to study it for only a day or two, and that will probably be all we need to know in order to go on further. Now, if you've had chemistry before, some of these things might be a little bit familiar. If you haven't had chemistry before, it's maybe not so much of a problem because most of what I'm going to introduce is fairly basic. But the main idea is to reconsider some of chemistry from a physics perspective. Some of the things that may have seemed strange when you've learned chemistry the first time will maybe seem a little bit more natural this time through. And this will give us sort of a foundation for understanding much of what comes later. So a good place to start is to realize that chemistry is all based on the Schrodinger equation. The Schrodinger equation solves everything. It tells you why the electrons stick to nuclei and why nuclei stick to each other and so forth. It's all the Schrodinger equation, but that's not actually a very useful way to think about things because solving the Schrodinger equation for more than 1 or 2 particles becomes impossibly hard, and you can never develop any sort of intuition of what's going on. So what we should do is we should think about very, very simple cartoon-level problems and try to figure out what the general rules are of chemistry from that. A good place to start is with hydrogen. Hydrogen, or more generally, a hydrogenic atom, meaning that it has a nucleus of charge G, some generally nucleus of charge Z, and 1 electron. And you'll remember from your atomic physics courses or your quantum mechanics courses that the eigenstates of this 1 electron are indexed by a number of quantum numbers, the principal quantum number, n equals 1, 2, 3, and so forth. The angular momentum quantum number, which takes the values 0, 1, 2, up to n minus 1. And these angular momentum quantum numbers are sometimes called S, P, D, F, G, and so forth, coming from spectroscopic notation. Now, for 1 chocolate bar, does anyone know what S, P, D, and F stand for? Sharp as S. That gets you a quarter. D is diffuse. Yes, you're almost there. 2 more. Principal. Someone said principal. Someone who got it? Who was it? Someone said it over there. It's you. Okay, so he gets it. So sharp, principal, diffuse, and fine from spectroscopic notation. Your chocolate. Sorry, stolen out from under you. G. Does anyone? 1 more chocolate bar. If you tell me what G is for. It's not for anything, actually. It's for giraffe. They just need another letter after that. Okay. Anyway, in addition to the angular momentum quantum numbers, M takes the values minus L to L. And then the spin quantum number can be plus or minus 1/2. The most important thing to keep track of is that if you have S electrons, S eigenstates, maybe, let's see, how should I say this? So an S shell, I guess, of eigenstates can hold 2 has two possible eigenstates. P shell, So why is it 2? Because S means L equals 0. That means M has to be equal 0, but the spin can be plus or minus 1/2, so 2 possibilities. With a P shell, there are 6. Because P means L equals 1. M can be minus 1, 0, or 1. That's 3. And then the spin can take 2 values. That makes 6. D gives you 10, and so forth. Now you have all these eigenstates in a particular atom. And then you suppose to yourself that you have many electrons in that atom, not just a single electron in the atom. Also, I should probably give you the energies as well. The energies of these eigenstates are minus the Rydberg over n squared times z squared if the charge of the nucleus is more than 1, plus small corrections, things like fine and hyperfine fine structure. But the main energy just comes from the principal quantum number. OK, so now you have a bunch of electrons in your atom, and you need to figure out which of these eigenstates you fill with electrons and which ones you leave empty. And there's several rules for figuring this out. The first rule is known as the Aufbau principle, which is basically just fill by shells. So when you add the first electron to an atom, you start in one shell, and you keep filling that shell until it's filled. When you finish filling that shell, you start filling the next shell, and you fill that one until it's filled. Now, in what order do you fill the shells? Well, you fill the shells by Madelung's rule. Madelung rule, which has a nice mnemonic like this. You write out a table: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, and so forth, 5p, ... And then you fill in this diagonal way. This one is first, this is second, this is third, this is fourth, and so forth. And this will be fifth, down that way. Okay? So this order of filling shells is what gives you the structure of the periodic table. So let's take a look at our friend the periodic table. Oops. I don't see the... Uh-oh. Help. Let's see. Stop. Okay, hold on. Oh boy, now we have a real problem. Stop. Oh. Okay. Well, okay. So the periodic table, let's go on and see if we can get this started up a little bit later. So everyone kind of know, you have in your head what it looks like, right? So you start out by filling the top row of the periodic table, which has hydrogen and helium in it. There's one electron fills hydrogen. The next one fills helium. Then you start the next row with lithium and beryllium. That fills up the second shell. Then you have the next 6 elements: boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, let me try this again. See if that's going to work. Boron, nitrogen, carbon, neon, fluorine, neon, and then you're filling the 2p shell, and so forth and so on, and you fill them in all this order, and that gives you the structure of the periodic table. But you might wonder to yourself, well, wait a second, why is it that we're filling the 4s shell before the 3d shell? Because according to that formula up there, the 3 shell should have lower energy than the 4 shell. And so what gives us the right to fill up 4s before we fill up 3d? And for that matter, why are we filling, periodic table, thank God. So there's the periodic table, and we fill in this order. There's the first shell, the second shell, 2s, 2p, 3s, 3p, and there's 4s. It's filling up before the 3d. You might ask the question, well, why is it we're filling up 2s before 2p? Because according to that formula up there, they have more or less the same energy. So the answer to this question is basically because V of r is not equal to 1 over r. It's not proportional to the Coulomb interaction anymore. Well, why not? Well, it's not just a single electron and a nucleus. It's an electron interacting with all of the other electrons in the atom as well as the nucleus. So as the electron gets closer to the nucleus, it sees more nucleus and less of the other electrons. And as it gets farther away, it sees more of the other electrons. So you can think of having some sort of effective potential, which is the interaction between the electron and both the nucleus and the cloud of the other electrons. So you need to modify the shape of this potential somewhat. And if you try to solve the sort of the radial quantum mechanics problem that you solved, for the hydrogen atom, but you change the shape of this potential, you'll all of a sudden discover that all these shells have different energies now. They shift around. And that's why the ordering of these filling of the orbitals is not what you would expect from just a simple hydrogen atom. Actually, as we're on the subject of the interaction with the other electrons, you might find it surprising that we can even describe the eigenstates of the hydrogen of a general electron the same way we can a general atom the same way we can describe the eigenstates of a hydrogen atom, because it's not just interacting with the nucleus, it's interacting with all of the other electrons as well. But the reason more or less you can do this is because you can treat all of the other electrons besides yourself as just some sort of spherical cloud. So it's still sort of a spherical problem, so it follows more or less the same rules, and you can still enumerate the possible eigenstates in the same way. Okay, so this is the general structure of the periodic table, and we can now move on to asking about chemical bonds between the atoms in the periodic table. Okay, there's filling up Madelung's rule. So there's a bunch of different types of bonding. There's a chart that looks like this in the book, which tells you 5 different types of bondings: ionic, covalent, metallic, molecular, hydrogen, and some of their properties and what causes them. It's probably worth familiarizing yourself with this chart. Over the next, today we're going to try to cover ionic and covalent. The other types we'll do a little bit later on in the lecture series. So the basic facts are on this. You should probably know these, but we will just start today with the simplest type of bonding, which is ionic bonding. Ionic bonds. And the principle of an ionic bond is basically that an electron is transferred from one atom to another, and then the ions attract. Then ions attract. So the kind of sort of reaction that we can have is a sodium atom plus a chlorine atom. An electron is transferred from the sodium to the chlorine, so we get sodium plus chlorine minus. And then now I have 2 charged species, and they attract each other to form sodium chloride. Sounds easy enough. Probably the easiest way to keep track of this kind of reaction, or to evaluate this kind of, analyze this type of reaction, is to think about the energies associated with each step. So one piece of the energy is the ionization energy, E-ionization, which is the energy to pull the electron off the sodium atom to make a sodium ion and an electron. So you start with the sodium atom, neutral. You pull the electron apart from it and put it out at infinity, and the sodium ion infinitely far away at infinity. And this will be the difference in energies, what's required to pull the electron off the atom. There's also what's known as the electron affinity, which is the energy that you get back when you put the electron on the chlorine atom to make a chlorine ion. And then the last piece is known as the cohesive energy, or the bonding energy, which is the energy you get out when you put together the sodium ion and the chlorine ion to get sodium chloride. Okay? So the total energy budget for this reaction is E-ion. The ionization energy, you get back the affinity energy, the electron affinity, and you get back the cohesive energy. And if the total delta E is less than 0, if delta E is less than 0, then you get a reaction. Then it reacts. The reaction goes forwards. Now, there's a couple of caveats about this kind of argument. The first caveat is that if you're a chemist, you are inevitably talking about Gibbs free energies rather than just energies. And the reason it's Gibbs free energies is because you're doing your experiment at finite temperature, probably room temperature, and finite pressure, your room pressure. We're going to think just as if we're doing everything at 0 temperature, 0 pressure. So we can just think about energies, but it's more or less the same thing. The second thing one should be warned about if you're reading books is that the word cohesive energy or bonding energy is used in several different senses in different books. Everyone agrees that a cohesive energy or bonding energy is the energy to put two things together, but not everyone agrees what those two things should be. So they'll talk about the cohesive energy for sodium chloride, and some books will tell you that the whole delta E is the cohesive energy, and some books will tell you that the cohesive energy is just the energy for putting together the sodium ion and the chlorine ion. So you'll get two different results depending on whether you're counting the whole delta E and calling that the bonding energy, or if you're just talking about the energy to put together the two ions. So that's another warning. The last warning is that the results that you get for bonding energy will be extremely different depending if you're talking about taking one ion of sodium and one ion of chlorine and putting them together to make a sodium chloride molecule, or if you're talking about taking lots of them and putting them together to make a whole big chunk of sodium chloride. And the reason for this is because your sodium atom, if it's either bonded to one chlorine or it's bonded to a lot of different chlorines, it will be a totally different energy depending on how many things you're bonded to. So that's another thing to keep in mind, to be careful about. Okay, so in this set of energies that we're trying to keep track of, probably the easiest thing to understand is the bonding energy or the cohesive energy, also known as the Madelung energy or the Coulomb energy, because this Coulomb energy is basically just maybe write it out. It's basically just the Coulomb energy between the relevant ions in your system. So I not equal to j, qi, qj over 4 pi epsilon naught distance between I and j. So qi is the charge on ion. This is charge of ion j. So if I have two ions j, I just take its usual the usual Coulomb. If I have two ions, one with positive charge, one with negative charge, I'm just summing up the usual Coulomb energy between those ions to get the cohesive energy. Now, this is a perfectly good way to express the bonding energy, or the energy you get by taking these two charged species and bringing them together. But it obviously, and actually it's fairly accurate as well for most ionic solids, gives you a very good estimate of the amount of cohesive energy you get by this definition. And so all you need to know is how far apart those ions are, and you know how much bonding energy you got. Of course, there's a little bit of a problem with this expression, and that is it goes to minus infinity if you bring the sodium ion and the chlorine ion extremely close. And that obviously doesn't make any sense. So what's really happening here, let's see, draw it like this. This is Rij for between the two atoms, and here's the energy. So this is the 1 over r curve that you expect for Coulomb interaction. And the actual physical energy you get looks like 1 over r, looks like 1 over r, and then at some point it shoots off way up to infinity. So this is actual. So if you know the distance between the two atoms, you have just by taking this energy here, which is the Coulomb prediction, it's extremely close to the actual bonding energy there because the shoot-off is extremely rapid. So what's causing this shoot-off to infinity? Well, when you start pushing two atoms really close together, you realize they're not just point charges anymore. They're going to start to overlap. Their orbitals are going to start to overlap. Pauli exclusion principle is going to get into the game because you're trying to put too many electrons in one place. And the energy just shoots right off very, very, very rapidly. But right here by the minimum, the Coulomb estimate is still a pretty good estimate of the cohesive energy. So that's pretty much everything we need to know about the cohesive energy. Now, what about the ionization energy and electron affinity energies? Well, the ionization energy or electron affinity energy have to do with the energy levels in the atoms. And in order to figure that out, we really need to solve the Schrodinger equation of those atoms, and, an electron in some effective potential, which has to do with the nucleus, and also all of the other electrons. It's kind of a hard problem. But even though we're not going to actually solve the Schrodinger equation, there's some trends which are pretty easy to keep track of. So this, if you've done chemistry, you probably know this already. But this picture of the periodic table shows you where the large electron affinities and the large ionization energies or small ionization energies are. It's also down here. So the small ionization energies are sort of down in this corner. The size of the splotch is how big the ionization energy, the smallest one being cesium or francium down here. And the large ionization energies way up here in the noble gases in helium. Electron affinities go the other way, with the exception of the noble gases, which have essentially no electron affinity. The highest electron affinities are way over here in this corner, up by fluorine and chlorine and bromine, over on the right-hand side. So if you want a good ionic solid, what you need, an ionic reaction, is you need to be able to easily pull the electron off of one species, and then you want to get out a lot of energy for putting it on the other. So you want a small ionization energy and a large electron affinity. So good ionic solids are things like, fluorine, sodium fluoride, rubidium chloride, things from way over here bound together with things from way over there. Now, chemists have an expression for this, that a shell of electrons, an atomic shell, wants to be filled. So if you have a shell filled plus one electron, like you would have in this first column, sodium has one electron in the 3s shell, potassium has one electron in the 4s shell. That shell is easily pulled off because the shell is most happy when it's exactly filled. Similarly, with fluorine, it's one short of being filled, so it has a high electron affinity. It wants to be filled. So can we understand a little bit? They're mostly filled shells on the right, and they have high electron affinity and high ionization energy. And on the left, it's small ionization energy and small electron affinities. So can we understand in some physical way why this is? Actually, it's not too hard to figure out why that is. At least roughly, we can make a cartoon picture of it. So let's try to figure it out from looking at sodium. So sodium, it has, if you look on this table, a periodic table, it has 11 electrons. It's the 11th element. So what does it look like? It has a nucleus of charge plus 11 in the nucleus. And then we have we have 10 electrons in the 1 and 2s shells. So we'll draw a picture of 1s and 2s, and 2p. And in the 1s, 2s, 2p shells, we have 10 electrons with a charge of minus 10. Then we have this one electron in the 3s shell out here. So this is one electron out here in the 3s shell. And to that one electron, if you imagine yourself being that one electron, how much nuclear charge do you actually see? Well, the total nuclear charge you would see, this electron sees Z equals 1. Why? Well, because these 10 electrons inside of it are more or less screening that positive charge in the nucleus. So it sees a charge of only plus 1. So if we wanted to use our hydrogenic formula to figure out the binding energy, we would say that the binding energy is a Rydberg times 1 squared over, this is a 3s divided by 3 squared, n squared downstairs. Now, this binding energy, ionization energy, is a little bit of an underestimate of the actual binding energy of the 3s electron. And the reason for this is because sometimes that 3s electron gets closer to the nucleus and realizes that, in fact, it's not a charge of plus 1. It's actually a charge bigger than plus 1. So it's bound a little bit tighter than this estimate would tell us. Okay? But basically, at some level of approximation, it's like one electron bound to just one charge. Does that make sense? Yeah. Okay. Now let's look at fluorine instead. Fluorine is a little more complicated. Fluorine, it's the 9th element right over here, almost filled 2 shell. So what does fluorine see? Well, okay, so we have the nucleus with a charge of plus 9. And then we have the 1s shell down here, 1s shell, which has a charge of minus 2. And then in the 2 shell, we have 7 electrons out here. Check it, the 1, 2, 3, 4, 5, 6, 7. 7 electrons. Now suppose and they're more or less at the same radius. because they're all in the 2 shell. So suppose you're this electron. What do you see? You see a charge of Z equals, well, maybe you see +7, because these electrons here aren't screening the nucleus, so you only see +9 - 2. Now, +7 is a little bit of an overestimate. You would then get a binding energy of a Rydberg 7 squared over, let's see, so this is a 2 electron out here, so it's over 2 squared, the principal quantum number squared of this electron. This is a huge overestimate of the actual binding energy in fluorine, because sometimes these electrons do get inside of this electron and screen the nucleus better than we would estimate here. But still, you see that there's a very good reason why it is an almost filled shell sees a big nuclear charge, and an almost empty shell sees a small nuclear charge. So this is behind the origin of why it is that we have this cartoon phrase that an almost filled shell wants to be filled, and an almost empty shell wants to be empty. Does that make some sense? Yes? Yes? Yeah? OK. All right. So it's basically an issue of how well screened the nucleus is. So this gives us a pretty good picture of what's going on with ionic bonds. There are differences in how much the electrons are, how much the atoms want to have an extra electron or want to give up another electron. And so if you have an atom like potassium and an atom like fluorine, the potassium is happy to give up its electron. The fluorine wants to get that extra electron. You get 2 ions. The ions then attract. So it's a great picture of ionic bonding. However, you also have bonding between two atoms that want the electrons just as much as each other. For example, O2. 2 oxygen atoms will bond with each other, and of course they want the electrons just as much as each other. So this brings us to the picture of what they call covalent bonding. Covalent bonds, which is okay. There's a chemists have this picture of covalent bonds, which they like to say that the atoms will share an electron, and because they're sharing electrons, that binds the atoms together. Now, can we understand a little bit better from physics what it is that we mean by this, that sharing electrons binds atoms together? So there's a nice picture of this, which basically comes from just particle in a box physics. All right, let's put it over here. Particle in a box. In box. And we're going to analyze hydrogen plus hydrogen goes to hydrogen 2, just based on what we know about particle in a box. Now, what am I talking about when I'm talking about a hydrogen atom being a particle in a box? Let's draw a little box here. That box is supposed to represent the attraction to the nucleus. So a hydrogen atom is basically its electron bound to the nucleus. So, okay, it's not exactly in a square box, but it's still some binding to the nucleus. So we'll put our electron in our box, give our box a size L, and the ground state energy of the hydrogen of the electron in that box of size L is h bar squared over 2m pi over L squared. Now we have another hydrogen atom here, so we'll give him a box size L, and he has the same energy, h bar squared over 2m pi over L squared. Now over here, where we have H2, we get a bigger box, maybe a size 2L for the hydrogen molecule. And so we have a ground state wave function for the bigger box here, and the ground state wave function has an energy h bar squared over 2m pi over 2L squared, which is lower. Of course, we have to put 2 electrons in this ground state wave function now, but we can do that because there are 2 spins, and we discover that this side of the equation is lower than the sum of these 2 equations. So what's going on here? What's going on here is that we're allowing the electron wave function to spread out from being confined here and confined here to being less confined here. And by letting the wave function spread out, we're lowering its energy. This is just Heisenberg uncertainty. You make delta x bigger, delta p gets smaller. With smaller delta p, you can have a lower kinetic energy. So by spreading out the wave function, you lower the kinetic energy. Now, we can consider the same thing with helium, and we'll see that actually something is very different about helium. So helium, you have a box, you have your ground state wave function, and you have 2 electrons in it. Here, again, a box, ground state wave function, put 2 electrons in it. And then the question is, does it go to helium too? Okay, now here we have a bigger box. We get a ground state wave function. We can put 2 electrons in it. Then we have to start filling up an excited wave function as well, because we filled the ground state wave function. So we have to fill this guy as well. And now we're not gaining so much. As a matter of fact, we're not gaining anything at all, because we had to, as well as filling the lowest energy state, we have to fill a higher energy state as well. The lower energy state is known as the bonding orbital. And the higher energy state is known as the anti-bonding orbital. So generally, bonding orbitals are ones whose energy is lower than the original wave functions, and antibondings are higher or equal to the original wave functions. So this is why helium, very roughly, why it is that helium doesn't bond, but hydrogen does. Now, this is obviously very cartoonish, but we can do a better job by using what's known as molecular orbital theory, molecular or atomic orbital theory, also known as tight binding theory, also known as linear LCAO, which equals linear combination of atomic orbitals, Now, I think if you took the atomic course last term, you may have even done this calculation. And we're going to do it again, but we're going to do it simpler than you did it last term. And the reason I'm simplifying it is so it's easier to see the physics underlying, okay? And we're going to use some of these techniques later on in the term, so it's good to make them as simple as possible. So the first thing we do is we imagine having 2 nuclei at positions R1 and R2. And, oops, okay. So I should tell you which problem we're analyzing. Right, we're going to do so the problem we're going to look at H2 plus. So this is 2 protons and 1 electron. 2 protons and 1 electron. I think you looked at this problem before last term. Okay. So we're going to see that allowing this electron to delocalize between the two nuclei is going to lower its energy and therefore form a bond between the 2 nuclei. Now, the first thing we're going to do is we're going to use Born-Oppenheimer approximation. Born-Oppenheimer. J. Robert Oppenheimer was the father of the American bomb project, not Bond project. And Max Born, we've discussed him already, one of the fathers of quantum mechanics and Olivia Newton-John's grandfather. For 1 chocolate bar, does anyone know what Olivia Newton-John's biggest hit song was? I'll give you a hint. It has something to do with the subject we're studying. Yeah, who said that? The same person? Okay, you get this one. All right, very good. Physical, yeah. 10 weeks at number 1. Okay. Anyway, so the Born-Oppenheimer approximation is basically fix R1 and R2. Fix the position of the nuclei and let the electron move. And that's okay because the nuclei are extremely heavy and they would move very slowly, so the electron can come to its eigenstate very quickly, and then you can sort of resolve it wherever you put the nuclei and look for wherever the nuclei have their lowest possible energy. So then we write a Hamiltonian for our electron, p squared over 2m, plus the Coulomb interaction with the first nucleus, plus the Coulomb interaction with the second nucleus, where V is the usual minus e squared over 4 pi epsilon naught r minus r1, so forth. I'm going to abbreviate this thing as this term is K for kinetic energy. This term is V1 for interaction with the first nucleus. This term is V2 for interaction with the second nucleus. Now, this is a hard problem because of both nuclei, but it would be a lot simpler if we just threw away one of the nuclei, pretend it's not there. Okay? So let's solve that problem first. So we can then have K plus V1 as our Hamiltonian, and we'll call the eigenstate 1, epsilon naught 1. So what's the answer to that problem? Well, it's just a hydrogen atom, on on nucleus 1. So 1 is the ground state of the electron on nucleus 1, the electron in the s shell, if you like. You can do the same thing for 2. So this is, if we only have nucleus 2, we would get an eigenstate on nucleus 2. So I can draw these if I want. So here's R1, here's R2. Then there would be a wave function here of the electron sitting there as if this guy weren't there. And then there would be a wave function there, 2, sitting there as if this guy weren't there. Is that clear? So the two states, the two atomic orbitals I'm thinking about is the electron on nucleus 1 as if nucleus 2 were not there at all, and the electron on nucleus 2 as if a nucleus 1 were not there at all. Good? Good? Yeah? Okay. So you can also think about 1 and 2 as being the eigenstates if the two orbitals of the two nuclei are taken very, very far apart, in which case you have two possibilities. The electron sits on orbital 1, on nucleus 1, or the electron sits on nucleus 2. And what we expect is going to happen is that when we bring them together, there's going to be a lower energy state, the bonding state, where the electron delocalizes between the two nuclei. And there may also be an antibonding state, antibonding, which is higher energy when we bring them together. And this kind of diagram is used a lot by chemists. It's known as a molecular orbital diagram. Molecular orbital diagram, which tries to keep track of what happens to the eigenstates when you start moving things together or apart. All right, so how are we going to solve this problem? Well, we're going to do it with the trial wave function, a variational trial wave function. And I believe you've studied variational methods before. So the wave function we're going to use is of the form phi1 times 1 plus phi2 times 2. And we're going to try to find the best coefficients, phi1 and phi2, which will lower the energy as much as possible. Okay, this is the variational principle. You try to get the best approximation to the ground state as you can by varying the coefficients arbitrarily. Okay? Now this actually gives the method its name. The name of the method, linear combination of atomic orbitals. That's exactly what we're doing. These are the atomic orbitals, and we're making a linear combination of them. Okay? It's also known as tight binding because the electron sitting on orbital 1, we think of it as nucleus 1, we think of it as tightly bound to nucleus 1, and this one is tightly bound to nucleus 2, and then we make some linear combination of those two. One of the reasons people really like this method of analyzing problems is because you can actually make the approximation more and more accurate by adding more and more things to the right-hand side with more and more variational parameters. So instead of just keeping track of two possibilities, the electron is on orbital 1, the ground state of nucleus 1 and ground state of nucleus 2, you can start also adding coefficients and other possible states the electron can be in, excited states on orbital 1, on nucleus 1, excited states on nucleus 2, and you make a bigger and bigger basis set. And as you make the possibilities on the right-hand side more and more, you get closer and closer to the exact wave function on the left. Okay, so now we have to actually write down our effective Schrodinger equation for this trial wave function. And that's something you're actually going to do for homework. I'll write out the answer. It looks very much like a Schrodinger equation. It's something you'll probably believe without too much justification. It looks entirely like a Schrodinger equation. The only difference is that this Hij, is a 2 by 2 matrix, Hj. I forgot to tell you something that we're assuming. Let me put it over here. So this is a bad assumption. Doing things out of order here. The bad assumption is that Ij is delta Ij. In other words, 1, 2 equals 0. Okay, that 1 and 2 are orthogonal wave functions. Now that's a good approximation if the nuclei are far apart, but if you put the nuclei really close together, it's no longer a good assumption. The reason we're making this bad assumption is because it makes our life a lot easier, and as in many cases, making this bad assumption isn't going to throw out the crucial physics. So we're going to keep this bad assumption for now. There's an exercise in the book if you want to go through it and do it more properly, but you'll get the crucial physics right by making this bad assumption, so we're going to go ahead and do it. I believe when you did it last term, you did not use this bad assumption, the algebra gets much worse. So it's going to try to keep the algebra as simple as possible by making that bad assumption. Given that bad assumption, this is the Schrodinger equation that you have to solve. And it looks pretty much like a Schrodinger equation. You know, there's a Hamiltonian wave function, energy wave function. The only difference is it's not the full Hamiltonian, it's just the Hamiltonian projected to our restricted space, which includes only the wave function 1 and the wave function 2. So it's a projected Schrodinger equation, if you like. So to solve this, all we need to do is we need to come up with, this is a 2 by 2 matrix, 2 by 2. In our case, we need to write out the matrix elements here. So let's do that. 1H1 is 1K plus V1. Do I still have the Hamiltonian? Yeah, the Hamiltonian's still up there. I hope it doesn't go off the board. 1 plus 1 V2, 1. This term is easy because 1, the ket 1, is an eigenstate of K plus V1. That's how we defined it. And its eigenvalue is epsilon naught. So in fact, 1 on 1 is 1. We define it to be. So this piece here just gives us epsilon naught. This part here, we don't know what that is. I'm going to call it V cross. And physically, what is it? V cross. We have an electron sitting on orbital 1 over here. And so here's the electron sitting on, and here's orbital 2. And V cross is the interaction between the electron sitting on state 1, sitting on nucleus 1, interacting with nucleus 2. That's what V cross is. I believe last term you may have called it direct interaction, or you may have called it J. Does that sound familiar from last term? Yeah, okay. The reason I'm not calling it direct and J is because in condensed matter, those words are used for something somewhat different. And I'm trying to avoid confusion about that, so I'm going to call it V cross instead. I mean, there's some relation between the two nomenclatures, but not enough that it's worth keeping it. So throw that out. We're going to call it V cross from now on. 2H2, we need that also. It's very similar. 2K plus V2, 2 plus 2 V1, 2. And again, this thing is epsilon naught plus V cross. The more interesting piece is 1H2, which is 1 K plus V2, 2 plus 1 V1, 2. Okay, so this thing is easy actually because K plus V2 is epsilon naught 2, and then 2 and 1 have been assumed orthogonal, so that gives 0. Okay, so that simplifies our life a lot. This one here I'm going to call hopping, and generally it's called minus T. I believe last year you called it exchange, and I probably called it kappa or something. So again, I'm not going to use that nomenclature because we use exchange for something else. Now, why is it called hopping? If you think in terms of the time-dependent Schrodinger equation, it's this kind of term that's sort of off diagonal, takes you from 2 to 1. So a hopping term can give dynamics to an electron, can take an electron that starts on nucleus 2 and lands it on nucleus 1. So it allows it to hop from one nucleus to the other, hence the name hopping, reasonable name. Okay, so given this, we're almost there. We have our 2 by 2 Hamiltonian matrix, epsilon naught plus V cross, minus T. Minus T, if it's complex, it would get a T star here. Then epsilon naught plus V cross is a nice little Hermitian matrix. We can diagonalize it. We get the eigenvalues, eigs equal epsilon naught plus V cross plus or minus absolute value of T. Now, I left off one little piece, which I'm now going to put back in. The thing I left off was the E nuclear, that the energy, the two nuclei are interacting with each other as well. So if I change the distance between the two nuclei, they would have some Coulomb interaction. But it turns out that E nuclear is very approximately equal to minus V cross. And that actually should be obvious from what you know about electrostatics. If you have a spherical charge, cloud of charge around another spherical cloud of charge, you can consider the whole charge as being at the origin, and the whole charge is at the origin is 0. The E cancels the plus 1. The minus 1 cancels plus 1. So it ends up these two pieces cancel each other. So I'm just going to write E plus or minus. The two possible energies are E naught plus or minus absolute T. So this is something that seems fairly natural, that the amount of gaining or lowering of the energy we get when we allow the electron to hop between the two orbitals is given by how much we allow them to hop. So by spreading out the electron wave function, you lower its energy. The more you spread out the wave function, the more you lower the energy. So we can even, maybe do it here. We can even write down the two eigenstates of this. If you diagonalize that matrix and find its eigenvectors, you would find that psi plus 1 over root 2, 1 minus 2. This is the antibonding, the higher energy antibond, the higher energy wave function, and then the lower energy wave function, 1 over root 2, 1 plus 2. And in fact, those forms of the wave function should look a lot like what we had in the particle in the box. So in the particle in the box, we had a bonding orbital, bond, here, and we have an anti-bonding orbital here, anti, here, with a node in the middle. And now we have two nuclei. The bonding orbital looks like this. It's symmetric, bond, and the antibond looks like this, plus, antibond. So it's very similar to what we have in the particle in the box. In both cases, the existence of the node raises the energy. Okay, so since the amount of energy you gain or lose depends on the amount of hopping, as a function of R1 minus R2, the distance between the nuclei, you might expect that the hopping goes up as you put the two nuclei closer together. So you would expect that the antibonding looks like this, the bonding looks like this, and that's more or less right. But actually, more accurate is something that looks like this, E R1 minus R2. Antibonding goes like this, and bonding goes like this. Again, when the two nuclei get too close together, it all of a sudden becomes extremely repulsive. And the reason it becomes repulsive is because a lot of our approximations break down. This approximation breaks down that the two atomic orbitals we're using are no longer orthogonal. And further, that statement I made up there about the two charge clouds canceling breaks down once the positive charge gets inside the other electrons. Once the other nucleus gets inside the charge cloud of the electron, then you can no longer cancel. You remember this rule that if you're inside some charge, you don't count it, and if you're outside the charge, you do count it when you're talking about spherical charge distribution. Anything that's inside you, closer to the center, you count, and you put all at the center, and anything that's outside you throw away. So if the nucleus gets inside the charge cloud of the electron, then it starts to see the other nucleus, and it starts to be repelled by the other nucleus, so the energy of the bond goes way up. One more thing here before we end. You can also consider a very similar physics if you have two different atoms. So we have hydrogen and fluorine, and here I've drawn one up here and one down here because their energies, if you just have an electron on hydrogen, it's much higher energy than the electron on fluorine. Or maybe I should have said sodium and fluorine. Sodium and fluorine, doesn't matter. Just on something that has a low ionization energy or wants the electron a lot less, and something with a high electron affinity or a high ionization energy wants the electron a lot more, and you can allow an electron to delocalize between the sodium and the fluorine. If you do that, the only thing that changes here is that these two energies on the diagonal become E sodium and E fluorine, like that. Okay? And those two can be different from each other. If you diagonalize this matrix now, you'll find two different energies again. So we'll draw that as a bonding and an anti-bonding orbital. So there's anti-bonding down here. Again, allowing the electron to go back and forth changes the total energy, and here's anti-bonding up here. But these coefficients will not be the same. For the anti-bonding orbital, this coefficient, beta minus alpha, will be bigger. Beta will be bigger than alpha. There will be a higher probability that the electron will be over here for the antibonding orbital, whereas for the bonding orbital, beta alpha like this, most of the weight of the wave function will be over here on fluorine. It's sort of a simple 2 by 2 matrix diagonalization problem. There's an exercise in the book on this as well. So the idea is that, but just by looking at this 2 by 2 matrix, you can see how you go from a covalent bond where the electron is distributed equally between the two nuclei to an ionic bond where really the lower energy orbital puts the electron almost entirely over here on the lower energy species. Okay, I guess I stop there and I see you tomorrow.